Okay, good deal. Mark Allen, I'm with ROHN Tower Company out of Peoria, Illinois. And if you notice, that slide says Smart Tower Systems. Smart Tower Systems is part of ROHN. Myself and another principal set it up about 2 years ago when we discovered there was a really big issue in trying to decide how towers really behave in the real world opposed to what the finite engineering analysis software predicts that they're going to do. Just as a little bit of setup as to what we're going to talk about here, it's no secret if you've looked at your corner cell phone tower, there are more and more antennas appearing on that on what appears to be a daily basis. The fact of the matter is, a lot of these structures were originally designed for one carrier. And as things have progressed along, there have been more and more needs to get on these structures. And the way engineers, and as you know, ROHN designs towers, the way the engineers design these is they use an empirical analysis program based on finite element analysis to predict how the structure will behave based on the loading that goes on and the ambient conditions, such as if you're in Florida, the wind loading is going to be higher than it is in the middle of Texas, for example. If you are a vertical real estate company, for example, American Tower or Crown Castle International, how do you make your money? Anybody? How do you make your money? Yeah, you rent space on these structures. And therefore, you are highly motivated to do what? Put as much as you can on there, which is great, except you want to do it in a safe and responsible manner. But these companies, who are all publicly traded, are under excruciating pressure all the time to generate the maximum amount of revenue with their assets, which in addition to stockholder pressure is just good business. Consequently, there is a need for this technology. So myself and our chief structural engineer, who is a fellow named Dave Brinker, who incidentally wrote most of the TIA specs himself for tower loading, decided that there was a better way to do it. So we basically broke the project up into two parts, and Brinker was responsible for the structural engineering side of it, and since I come from a product development background, I was responsible for the hardware side of it. And at this time, I'd like to introduce Al Spindell, who is standing right here with me. He's one of our senior scientists on the project, and he is charged with actually bringing the hardware to life. I've got samples of the hardware here we're going to pass around in a little bit, but here we go. By the way, it's a pleasure for me to tell you this is the first time we've really talked about this in public. The lawyers finally turned us loose after sufficient patent aggravation and other problems. So when you look at this slide, you ask yourself a question, or you should, you know, is that tower overloaded or not? Well, if it's a nice morning like it is outside right now and the wind's not blowing and there's not 6 inches of ice on anything like there is in my backyard in Illinois right now this morning, probably not. So we decided that it was really time to go beyond the guessing and the empirical analysis and start tempering these things with real-world measurements. So here's what you get when you can get into continuous health monitoring. You can determine the amplitude of the vibrations, and if any of you have any sort of mechanical background, you know that every mechanical thing has a natural vibration frequency. We correlate displacements with wind and other conditions. In other words, if the finite element program said at X miles an hour the structure should move this much, by the way, do you think towers move in the wind? How many people think they do? Okay. How many people think they don't? Well, they do. And probably in some cases, the amounts would shock you how much they move. There are certain towers that I have measured that move as much as 6 feet at the top. And that's a lot of motion. Okay? We need to determine the dominant frequencies because we got a bunch of electronics people here. What happens when things come into resonance? Yeah, we know. Yeah, a lot of things can happen, particularly if it's something that's not supposed to come into resonance. Some large structures and buildings have active dampening systems on them, most notably in earthquake zones. The Asians are way ahead of us in this. Practically any building over 10 stories in the Far East has active dampening systems. And these are used to some degree on structures here, most notably the Hancock Tower and the Sears Tower, which is now called the Willis Tower in Chicago, both have large broadcast arrays on top, and those are dynamically dampened arrays. Because if you think about it, the building itself moves, then the antennas move as well. And because the building is square or rectangular and the antenna structure is cylindrical, they move in different ways under different conditions. And then, of course, if you happen to be the owner of that structure, you'd like to be notified when there's an issue. If you measure data over a long period of time, you get a benefit, and that benefit is trend analysis. So if it behaves like this when you built it, and 5 years later it behaves like that, there may be a correlation to the fact that you need to do some maintenance. Okay, early detection of structural issues and mounts. As things twist and move and shift, metal fatigues and it cracks over a period of time. And we actually have been successful in detecting changes in the structures when cracks become apparent. Admittedly, they have to have advanced, but hopefully we can catch them before it's something catastrophic. Detection of additional appurtenances. An appurtenance in this particular case means an antenna or an antenna mounting structure. And if you're a tower rental company, you probably don't want somebody just showing up one day and sticking something on your tower because probably they don't want to pay you for it, number one, and number two, it could adversely affect the loading. So if somebody comes along and sticks another appurtenance on there, what's going to happen? Those long-term trend analyses we were talking about are going to change. Okay, the sensors are so sensitive we can detect actually people's footsteps as they're climbing. Nowadays, tower maintenance people have to call a network operations center and say, hey, we're here, we're opening the doors, we're opening the gates, we're getting on the tower. And we can either verify that they're there or somebody's there that's not supposed to be there. Vibration mitigation we've really already talked about. However, there's a really nasty phenomenon called vortex shedding. And this happens when two structures are very close to each other. They come into a parallel resonance. I'm not a structural engineer, so all I know is what the result is, and it's bad. Fatigue, crack, growth detection we've really already talked about. And then this particular sensor, this is actual sensor that goes up on the tower. I'm going to pass this around for you to look at. But this sensor is self-powered for about 40 to 45 seconds once the ground unit is cut loose from it. Consequently, it will detect the last 30 or 45 seconds of that tower on its way to the ground, which could be used in forensic analysis either by authorities, the insurance companies, or the owners. All right. Essentially, the way to predict how a tower is going to behave is to do a full-scale wind test, but you really can't do that. So we do it with software. But this gets you a lot closer because if your prediction said tower ought to move 6 inches with this amount of junk stacked on it, and it moves 6 inches, then you know that you got your analysis correct. If it only moves 3 inches, what does that tell you? Software was conservative. Let's put more antennas on it. Let's generate more revenue. Tower mapping is a process that companies go through. It's also called an audit, where they have someone climb the tower and look at everything that's on there and catalog it, because things tend to creep on and creep off over a period of time. once again, since if we measure this initially, then we can see how the tower is behaving as changes take place along the way. And we can determine without the benefit of a physical inspection whether something's been added or taken off. Shielding and drag factors have to do with where a tower is mounted on the terrain, whether you're on the uphill side of a hill, the downhill side of a hill, sitting out in the middle of West Texas with nothing around, and so forth. This data can all be used for percentage of utilization, as I mentioned previously. Where you put things on towers matters. Typically, towers are beefier in the bottom than they are at the top. So you can add a lot more stuff lower down on the tower than you can at the top. And there's quite a science to figuring out where these appurtenances or mounts go. And with the real world data we get out of this thing, we can help them figure that out. Increases the value of the tower for critical services. You might have noticed that some of these towers have an abnormally large number of microwave antennas on them, particularly in cellular systems. Obviously, that's a hub in the hub and spoke system. Consequently, the loss of that tower would create a significant network issue for the carrier. So that might be designated as a high value or critical tower. And those are ones they'd probably want to monitor first. Potentially, if you're renting that space, and you can use that as an advertising tool to tell a prospective customer, like a law enforcement agency or government agency, that, hey, this tower is 100% monitored, that might be a selling point. And then ROHN, as a designer of these structures and other companies, we use this data, which in a raw basis for future designs. Look at this problem. Let's say, for instance, you're just about along the Georgia-Florida border there, and you're a tower company that's got 400 or 500 towers scattered around where this is going to hit. There's a big question that should be in your mind. You know, what's going to get damaged, to what extent, and where do I send the 10 or 15 crews that I have available? Well, we can tell you, because the thing that we're really looking for is all towers displace when wind blows on them. But if something displaces and it's a rigid structure, what do you want it to do when the wind's through blowing? Yeah, go back where it was. So when it doesn't, we call that permanent critical displacement. And if that's serious enough, that's where you send your crews first, because those structures could be in danger of further deterioration or potentially collapse. I'm going to move through these really quick because there's a lot of stuff here. Okay, here's what we measure. Lateral displacement, back and forth, twist and sway, and rotations, dominant frequencies. We can integrate this with ice sensors, wind sensors, and other types of sensors. We correlate this with on-site weather data we move and then we measure, and then we overlay that on top of National Weather Service data that's available. And we've developed some mathematical algorithms which are really unique to these structures that predicts this behavior based on the weather input. And the trend analysis we talked about earlier, but this is particularly valuable when you look at things over multi-year periods. Okay, here were the problems when we got ready to do this. If you think about this for a minute, we've got this tower sticking up, and we got a sensor up on top of it, and it has no reference to anything. And that's a big problem, because how do you really tell when this is moving? We started thinking about who else has this kind of problem. And after more consideration than I care to admit, we came to the conclusion. Anybody want to guess? Geologists, that's not right. I didn't hear the answer I was looking for. NASA has this problem, okay? So it turns out that after racking my brain, I remembered that I had an old college roommate that went to work for NASA in guidance systems. So I called him up and I said, how do I solve this problem? And he said, you know, we got this little thing up there called the Hubble telescope. And he said, they have nominal pointing accuracies that'll absolutely amaze you. Let me put you in touch with the guys that designed that guidance system, because they've solved this problem. And they did, and I talked to them and basically got some ideas on how to solve this. And we came up with this thing, which is actually technically classified as an inertial measurement unit. And for those of you that know much about sensor technology, all sensors have bias problems, they have noise, they have other problems, and at some point they have to be reset to a zeroed out point. And all these problems, I'm not going to go into the details because I can't, but there are some significant issues in making this thing accurate. So the question is, how accurate is it? We can measure measurements reliably down to probably about 1/4 of an inch of movement, which is plenty sufficient for what we're trying to measure. And that's in all 3 axes. Okay, the other problem was, if you're going to take one of these and mount it on top of my tower in amongst all those cell phone antennas and stuff, it can create what kind of emissions on its own? Yeah, 0. This thing better not contribute to the noise floor on the tower. Tower companies were very concerned. They said, look, we're going to have every cell phone company on the planet squawking at us that whatever that thing was you put up there is desensing their equipment. So I'll show you how we got around that. When you're mounted on top of a tower, what's another problem? This thing gets hit by lightning all the time. So how do you make something that's basically immune to lightning? Okay, you don't, it's the short answer, but we can take precautions. We had to accommodate a wide variety of mechanical installations. These go on poles, they go on square poles, round poles, hex poles, triangular towers, every kind of mounting configuration you can think of. And then, needless to say, it's got to stand up to the weather. So who did I put together to do this? Well, it's a pretty interesting team. We got a physicist, we got a mechanical engineer, we got structural tower guys, electrical people, RF people, software folks. This is all digital signal processing driven, so there's some DSP, PhD types. And then we have a sensor fusion person who is basically the ringmaster and brings all these elements together. This is a photograph from our original conceptual engineering meeting. It was held up in Peoria where my office is. The guy in the picture on the right-hand side is Dave Brinker, I referred to earlier. He's our chief structural engineer. And as you can tell, he's into math. So here's how it works. The red triangle at the top of the tower is this thing. And these are connected. There can be, on average, typical 300-foot tower, there's going to be 2 sensors, one at the top and one at a midway point. And then we may put a wind sensor on there as well. Without going into the reasons, the sensor really is supposed to be 30 feet off the ground, and that's what the standard calls for. And we connect it all together with a heavy-duty armored Cat6 cable, but we don't use internet protocol because there are distance limitations. So we went to another protocol. So this is kind of the top level. By the way, we went to RS-485, it's listed there. Okay, here's a diagram of how the thing works. You got the sensors on the tower, you got a GCU, or ground control unit. This is the circuit board out of the ground control unit. And It has sufficient disk space in that box to store several months worth of data, depending on how we have the sample rate set up. And from there, it's connected to the internet either through a 4G radio or through land, traditional copper internet. Stepping up a level in the architecture, you got all those towers on the left-hand side. They go through an internet connection through the cloud to a primary and mirrored server, and then the user community down at the bottom connects into the same server and they get their data. So what were some of the features we were looking for? How am I doing on time? Okay. High voltage and current, RF protection, functions in severe weather conditions, and so forth. Let me get down to the bottom. It had to be simple to install because typically it's going to be put up by a tower installer who is basically a non-technical person. And it has to be scalable, and we have to be able to upgrade the software in these things without climbing towers. Okay, there's what the sensor looks like. I'm passing one around right now. You can take a look at it. There's a universal mounting bracket on the left-hand side that matches up with the sensor. And if you'll notice on the bottom of the sensor, there's 3 potential connections there. One comes from the ground, the other one daisy chains through and goes up to the next sensor, and the third hole is for an auxiliary device like an ice sensor or anemometer. And that all streams together into the same data stream. And that bracket pretty much fits about 90% of the installations. So when you look inside the guts, starting in the upper left-hand corner, there's the onboard microprocessor. The Keep Alive power supply, that's the one that takes care of you as you're going down to hit the ground. There's 3.3 volt supply there. Then all this, the gasket, which I didn't pass around, is an EMI type gasket. Keep all the noise inside. Then we've paid pretty direct attention to lightning on the power supply plus the 485. And then over on the right-hand side up there is the RS485 comms processor. This is the actual inertial measurement unit. It has 3-axis gyroscopes in it, accelerometers, and lots of other neat stuff. It's kind of the secret of what makes the thing operate. Of course, it's MEMS, which is significantly quality-wise upgraded device, very similar to what you got in your cell phone. When you rotate your cell phone, it tells you which way is up and turns the picture sideways and all that good stuff. There's the I/O connectors. This is actually upside down. There's the I/O connectors at the top, the gasket again, and then there's your 6-axis IMU. That's on the vertically spaced board there. So we really needed to make sure the testing was good, and it dawned on us that the people that know more about testing things in lightning environments than anybody else are aircraft people, because most of your aircraft nowadays are fly-by-wire, and aircraft get hit by lightning all the time, so we figured, who would know more about this situation than those folks. So we contracted with the people that Airbus use, and Lockheed Martin, which were about the best guys we could think of, and we went and did all this testing. There's one of the sensors there, and that's mounted to a section of our tower, and that's getting all set up for a lightning shot. This is the other end of it where they measure the current coming off the other side. By the way, FAA DO 160 is the standard they test the aircraft to. And since there is no standard for exactly what we do, we took the most stringent one that we could come up with. There's the generator. It makes a really loud pop when that thing's discharged. By the way, they don't let you stand too close either. Okay, here's where we're doing essentially FCC Part 15 test. We're looking for unintentional radiators. We checked it from 3 megahertz to 3 gigahertz, and then all the multiples that are relevant past that. And it's tight. course, when we mount it in amongst a bunch of antennas, what are you going to get? A lot of RF energy up there. So we tested this thing to a level of, any guesses on volts per meter? 100 volts per meter, which is the max their equipment would go. And we really didn't have any problems. Okay, there we are at higher frequencies doing the testing. This is a fold-over tower at our test facility. It's a 60-foot tower. There's Alan standing right over here. This was sensor installation number 1. This was the prototype, and there it goes. That's what it looks like installed. And it's still going. There's the artist concept of the ground control unit. That's what it looks like in real life. And basically it's just a cabinet. And inside you've got the local CPU, fancy name 4A, computer. And with the ground control board that I'm passing around is right there in the middle. Power supply is at the top. The 4G radio is up at the top. And batteries at the bottom. So it's really pretty straightforward. All right. How am I doing on time? We're okay. We're perfect. Between Alan and I, we'll try and answer any of your questions. Have at it. Yes, sir.
Are you providing monitoring services for this product as well, or is that everybody puts their own knock together?
Well, it's interesting you'd ask that question. For those of you that might not have heard the question, it's are we doing monitoring services or the customers doing them themselves? There's actually a combination. The smaller tower owner operators who really don't have a need for the specific knowledge, they're really interested in just, do I have a problem or not? We're providing that as a value-added service. The larger 4 or 5 tower companies in the country here who have engineering staffs of their own, they want the raw data and analyze it themselves. Does that answer your question?
Yes, it does. Thank you.
Yes, sir. Next question, right up here, up front.
Tower height. What's the tallest tower that you've actually put a sensor on?
320 foot at the moment, but we are in the process of getting ready to go on a 2,000 footer down in Houston, Texas. One with a big candelabra on top, 3 television.
I was wondering, we have some 2,000 footers out where I live right here, and how much they actually move.
They move
Well, I know
a
they
lot.
move a lot. I've been on top of one, but I just was wondering how much are actually moving over what the engineering says they're moving.
That's what they want to know.
Now, we basically designed the system where it can go on a 2,500-foot tower, which doesn't exist. So if someone manages to build one that high, we can accommodate it.
Yes, sir, right behind you.
Is your monitoring data, is that SNMP compliant so that you could bring the monitoring information back into like a network manager of managers, or is it a dedicated system?
Yes, it is.
Absolutely. We can generate SNMP traps, and basically what happens is this local PC that you see that's installed at the base of the tower, that communicates using a publish-subscribe protocol up to the cloud server, which you saw in the network diagram there. And you can set any types of parameters on any data set that we generate out of that ground computer to generate an alarm if it exceeds the threshold. And then that goes up on a proprietary publish-subscribe protocol to the cloud computing center. And then that can generate an SNMP trap, can generate an email, or simply be logged. And there's a user portal where you can log in and see events which occur, for example, an alarm threshold being exceeded, or you can actually request high resolution data sets. So let's see that, you were on vacation in the Caribbean and you come back and you see, oh gosh, 2 weeks ago there was a wind event which caused a displacement to exceed a threshold. And you can go back and download high resolution data, generate graphs or whatever. And the system does generate graphs and things for you, but it also allows you to when an event does occur, to download high-resolution data for your own analysis.
Thank you.
Oh, we got your mic. Next question, please. Yes, sir.
Notice one of the slides said low cost. What do you consider low?
Yeah, I don't think he quite got to you with the mic. He said low cost is how low?
Yeah.
We're looking at, on a typical installation, hardware cost of under $5,000.
Okay.
Not suitable for home use.
Not really.
Compared to the cost of a new tower, though, it's going to be very cheap.
There's one right behind you, and then you, sir.
Do you push that? Is there available for a push coming out of your servers to push it out to a network management system? I'm looking at the countywide or statewide radio system where you could pull all of that information right into the network monitoring system for the.
It really depends on your
Use the
own
mic, man.
enterprise threshold of pain in terms of how much you're willing to pay to transport that data up to a cloud layer where then you can retrieve it using high bandwidth connections. What we have found is that the vast majority of tower sites, even though there's some type of a network hub, the tower owner doesn't actually have access to that network connection there at the site. So most of this has been designed around using a GSM type or 4G modem there at the tower site. So obviously there's a very high transport cost for data bandwidth using that mode of data transport. If, for example, however, a small enterprise customer such as yourself on a countywide, say, first responder basis has a way to get higher bandwidth connections to those individual sites, then we can set up parameters in the system to push whatever resolution of data you want up to the central server. It's up to the customer's threshold of pain.
Yeah, typically we're looking at like 155 meg microwave available.
Well, then in which case you can have the full resolution data, which is 400 megabits per second coming out of the sensors.
Okay, thank you.
There's one right ahead of you here.
What is the process if I have an existing tower and I'm interested in buying your product? Do you start from what you do on the structurals on it first, and then come up with the what the initial parameters should be?
Well, we actually don't care what the original structurals were. What we do is we'll go on the tower, we'll take a baseline set of measurements, and based on our experience as tower designers, we determine whether or not we should be, or more precisely, you should be concerned about what's going on your tower. Okay? And then we use that as a baseline from that point going forward.
Okay. Good. Thank you.
Yep.
That was my question.
Okay. Anything else? Golly, one or two things. Either you didn't understand a thing I said or I answered all your questions.
Door prize? Sticker underneath?
Yeah, it's been circulating around there. Last call for any questions. Back in the back there.
Are you marketing this now?
We actually are about to turn on a website here in the next couple of weeks. We literally have been in a testing phase for over a year on this stuff. We had to be really sure that the data that we were getting off the system from various sensor types was accurate and traceable, and we could correlate it to what the structural design was. So we've satisfied ourselves at this point. Plus, we finally escaped all the lawyers. Okay.
That was the hardest part.
Anything else? All right, well, thank you very much. I appreciate your attention.